All right, 9.2. I just got a doc-cam, a PDF doc-cam, and so this may be the last video lecture that I do in this format. I might be doing them like on using like a webcam on a computer in the future. Anyway, I think it'll be nicer, but hopefully. Anyway, we'll see. But let's look at 9.2. Okay. So 9.2 is very similar to 9.1. We're going to be estimating a population mean in this section. In 9.1, we were estimating a population proportion. And what I want you to do is cross out this first part. Okay? I'm having you cross it out because I never want you to use this formula. Never, ever, ever. You would use this formula for estimating a population mean if you knew what the population standard deviation was. But you probably won't know what the population standard deviation is if you don't know the population mean, okay? Because in order to compute the population standard deviation, you have to know what the population mean is. So how would you have the population standard deviation without knowing what the population mean is, right? So of course you can never, it's like, I cannot think of a scenario where you would ever be able to use this formula. Okay, so cross it out, forget about it. What we are going to do is we're going to use the sample standard deviation instead of the population standard deviation. That's going to introduce more uncertainty into our calculations. And so we're going to need larger critical values to compensate for that. So instead of using critical values from the normal distribution, we're going to use critical values that come from a distribution called student's t distribution. And student's t distribution is similar to the normal distribution in some ways, right? It's bell-shaped, it's symmetric, it's a curve that never touches the x-axis, but it's also different in some ways, right? The variance is greater than 1. With the standard normal curve, the variance was equal to 1. The t distribution is a family of curves based on the concept of degrees of freedom, which is related to the sample size. To be specific, the degrees of freedom that you have for student's t distribution is always 1 less than your sample size. So if your sample size is 50, then you have 49 degrees of freedom, right? As the sample size increases, the t distribution is going to look more and more similar to the normal distribution. Okay, and I'll pull up in a second. I'll pull up in StatCrunch the normal distribution and the t distribution, so we can just kind of compare and contrast that. Okay, but the interpretation of t is the same as the interpretation of z. Right? It's the number of sample standard deviations that x bar is from the mean. Okay, to find critical values corresponding to student's t distribution, we're going to go to stat, calculators, and then t. Right? We're going to use the t calculator instead of the normal calculator to do this. Okay, let me give you a couple examples of this. And this way we can look at the t calculator in StatCrunch, right? It says find the following t value. So we want to find this t critical value, t sub 0.2, and this t value, t sub 0.10. Okay, let's go to StatCrunch to look at that. Okay, so what we've been doing is we've been using the normal calculator, right? The normal calculator is under stat, calculators, normal, and it's that old familiar curve that we are all used to, right? That we all know and love. What we're going to do now is we're going to go to the t calculator. So we go to stat, calculators, t. And you'll notice that it's shaped a little differently. It looks sort of like a normal distribution, but it's shaped a little different. And this thing is the shape of this is gonna change depending on the degrees of freedom you have. So if you have 50 degrees of freedom, then it starts to look more like the standard normal distribution. If you have 500 degrees of freedom, then it really starts to look like the normal distribution. If you have 5,000, right? They get more and more similar looking. Okay. We're in example 1a, we want to find t sub 0.2. And it says find t sub 0.2 where n equals 10. Well, remember, so df stands for degrees of freedom. The degrees of freedom that you have for student's t distribution, like I said a second ago, is always one less than your sample size. So if your sample size is 10, then you have 9 degrees of freedom. So we're going to put in 9 for the degrees of freedom there. And then we're looking for t sub 0.2. So for t sub 0.2, we want an area to the right, and we want that area to equal 0.2. Okay, so change that inequality so it's pointing right. Change this area so it's equal to 0.2. Hit compute, and there's our critical value. It's about 0.88 or 0.883. Okay. Now let's do part B. Part B says find t sub 0.10 with 15 degrees of freedom. Notice that in part A, they gave us the sample size, so we had 9 degrees of freedom. In part B, they're just giving us the degrees of freedom, right? They're just telling us you have 15 degrees of freedom. So your sample size was 16 in this case, but we're just going to use 15 degrees of freedom when we go to StatCrunch. Okay, so we want a critical value that comes from the t distribution, so we're going to go to Stat, Calculators, t. We want 15 degrees of freedom. We want an area of 0.10. So that number, that critical value, so t sub 0.10 is approximately we'll say 1.341. I think we usually round these critical values to 2 decimal places. Here I've rounded to 3, but anyway, that's the idea. Okay, so with that in mind now, here is the formula that we're actually going to use to compute a confidence interval for the mean mu, right? So we're going to say it's the point estimate, which is our sample mean in this case, plus or minus our margin of error, which is again, the critical value times the standard deviation, right? Sigma, or S, divided by square root of n. Okay. Just like when we're constructing confidence intervals for the proportion, we sometimes have to, or we should check conditions every time. I usually skip that step, but we should check conditions every time. It's the same way here. We have some conditions that we need to check. We can construct this interval assuming that x bar is normally distributed. Well, we talked in 8.2, I think. We talked about, no, it was 8.1. In 8.1, we talked about when exactly x bar is normally distributed. And we said, well, x bar is going to be normally distributed if either the data comes from a population that's normally distributed, or if your sample size is large enough. Okay, if your sample size is not large enough, you could maybe check to see if the data comes from a population that's normally distributed by looking at a normal probability plot like we did in 7.3. Okay, so this kind of ties everything all together, I suppose. Okay, but let's just look at an example. Let's construct an interval. Okay, so this one says the NCAA reports that the mean number of hours spent per week coaching and recruiting by assistant football coaches is 70. So they spend 70 hours a week doing their job. A random sample of 50 assistant coaches showed the mean to be 67.86 hours with a standard deviation of 8.2 hours. Okay. So the NCAA claims that their coaches spend 70 hours a week coaching. A random sample of 50 coaches actually showed that that number was 67.86 hours. All right, now we're being asked to construct a 99% confidence interval for the population mean. Does your interval support the claim made by the NCAA or does it cast doubt? Well, let's see. Okay, so our confidence interval is going to use this formula right here, right? So we're going to say our confidence interval is going to be x bar plus or minus t sub alpha over 2 times s over the square root of n. Okay, so let's work on t sub alpha over 2 for a second, right? Remember that alpha is related to our confidence level. Our confidence level in this case is 99%. So since our confidence level is 99%, that means that alpha is 0.01. Okay, 100% minus 99% is 1%. 1% is a decimal, is 0.01. If alpha is 0.01, then t sub alpha over 2 would be t sub 0.01 divided by 2. That would be t sub 0.005. Now we're going to go to the t calculator to figure out what that value is. When we do, they're going to ask us how many degrees of freedom we have. So let's see. Degrees of freedom. Our sample size in this case was we had a random sample of 50 assistant coaches. So our degrees of freedom should be 49. Okay, so let's go to the t calculator now and find this critical value. Okay, so 49 degrees of freedom. We want the area to be 0.005. Okay, so to 2 decimal places, our critical value is 2.68. 2.68. Okay, we're ready to plug stuff in, I think, right? So we've got our confidence interval here. We just need to plug stuff in. So x bar, let's see, what was x bar? It says, so x bar is our sample mean, right? So reading through the problem again, it says a random sample of 50 assistant coaches showed the mean to be 67.86 hours. All right, so x bar, 67.86. T sub alpha over 2, we just computed that. It's 2.68. S, right? S is our sample standard deviation. It says the sample had a mean of 67.86 and a standard deviation of 8.2. So the sample standard deviation is 8.2. And N is our sample size. Okay, and we said it was a random sample of 50 coaches, right? So N is 50. Oh, I'm sorry, this should be a plus or minus. Okay, so I'm going to punch this stuff into my calculator and write down the answer in a second step. So I'm going to have 67.86 plus or minus. Let's do 2.68 times 8.2 divided by square root of 50. That comes out to about 3.11. So our confidence interval, remember we're going to take turns first subtracting the number and then adding the number. So I'm going to have 67.86 67.86 minus 3.11. That comes out to 64.75. And then I'm going to do 67.86 plus 3.11. That comes out to 70.97. Okay, so there's our confidence interval. All right, now we had a follow-up question, right? They asked us to construct the interval, and then they're asking us, does your interval support the claim by the NCAA, or does it cast doubt? Why? Well, what's the claim made by the NCAA, right? Their claim is that coaches spend 70 hours a week coaching. Our sample mean was a couple hours less than that. Is that enough to say that the NCAA is exaggerating, right? That their coaches really don't spend 70 hours a week coaching? Well, here's our 99% confidence interval, right? We're 99% certain that assistant coaches spend somewhere between 64.75 hours and 70.97 hours coaching each week. So we're 99% sure that they spend somewhere between this number of hours and this number of hours coaching. 70 is within that interval. So 70 is within, it's within a sort of a reasonable doubt, right? So we would say, no, this does not cast doubt on the claim that the NCAA makes, right? Our interval supports the claim. So we say, yes, our interval supports the claim made by the NCAA since 70 is in the interval. Okay. And that's it for that question. Let me start a new video.